So we'll continue. I will again start sharing. So we have one more person joined. So okay. So where were we? We were at the design of a not constant. Yes, design of a concentric spring. So what we have seen is that we have seen what is concentric spring, why it is required. Okay. I hope you guys can hear me.
Yes, sir.
Okay, fine. So we have seen what is concentric springs, why concentric springs are required, how we will use them, know how what is how to know for the design, how we will put them. So if we want a uniform but more load but uniform stiffness, then we'll keep both the springs of equal length. But if we want a variational stiffness, like stiffness of one value up to certain load, after that load another stiffness, that time we will have a spring like this. One spring will be having a more length than the other spring. That time what happens, until the both lengths are equal, the load will be taken only by one spring. So it will have A to G stiffness, and from when the lengths are equal, after that both the springs will start taking the load. So G to H will be the stiffness. So that's how the combination of the spring will work. Now, for the design of a concentric spring, we assume that both springs are of equal length, of equal material. Few assumptions are there, and then we will start working on the what you can say combination of spring, concentric spring. Okay. So what we will assume, the springs are made of the same material. Now this is for the value of G and all that. So we will assume that spring is made of the same material. So both of them will have same value of G. Maximum torsional shears induced in outer and inner springs are equal. So tau is same. So we can match. Now since we are taking an example of this spring which are in concentrated form. So the inside spring dimensions are small d1 and capital D1. Small d2 and capital D2, and outside is small d1, capital D1. So here D1, capital D1, D2 are the mean coil diameters of outside and inside, and capital small D1 is wire diameter of outside, and small D2 wire diameter of inside. So C is the basically gap between these two springs, right? Basically distance between these two springs. Now, what is the assumption? First, they are made of the same material. Tau is same for both of them. They have same free length. So length is same. So now it will be a from the very first moment when the load is applied, they will start having a deflection. So deflection is a combination of both of them, and both are deflected by same amount. So therefore, they have same solid length. So their deflection of both springs is same. So same solid length means when the coils are touching each other, when it is completely compressed, that time the length, solid length of the spring 1 is equal to solid length of spring 2. So what is solid length of the spring? N into D. So D1 into number of coils, that is a D1 into N1 will be the solid length of outer spring, and D2 into N2 will be the solid length of inner spring, right? So they are saying is what N1 D1 is equal to N2 D2. I'm talking about small d, right? Okay. So now we'll use these like assumptions, and from each assumption we can use it in formula, right? So let's take we talked about it. D1 is a small wire diameter of outer, D2 is wire diameter of inner. D1 similarly, capital D1 is mean coil diameter of outer, capital D2 is mean coil diameter of inner. P1 is axial force transmitted by outer and inner springs, P1 and P2. Now since these are in parallel, right? So when the springs are in series, one after another, we have seen load is uniform throughout the spring, but the deflection is different. But since these springs are in parallel, so load taken by each spring will be different, but the deflection is same, right? So P1 and P2 is the load. That's why we are saying P1, P2 are the two different forces taken by two different springs, inner and outer, and P is the total force. So P is equal to P1 plus P2. Now delta deflection of outer spring and deflection of inner spring is delta 1, delta 2. Now deflection of both springs are same. Delta 1 is equal to delta 2, right? Number of active coils in outer N1 and N2 is number of active coils in the inner spring. Okay. So these are the configurations or the dimensions we are going to use, and then we will do the design of the spring. Okay. So now since assumption number what 2 is what maximum torsional shear is same. So tau 1 is equal to tau 2. Now tau is given by k into 8 pd upon pi d cube, right? Shear stress in spring is given by k is wall factor into 8 p1 d1 upon pi d1 cube is equal to k2 into 8 p2 d2 upon pi d2 cube. So now here we will assume that wall factor is same. Now wall factor is what 4c minus like what that formula we see 4c minus 1 upon 4c minus 4 plus 0.615 upon d, right? So that upon c actually. So that wall factor we will assume that wall factor is same for both the spring, and then later we will also prove that it is same. But here let's assume that it is same. So that time k1 is equal to k2, so k will cancel out, it will cancel. So we'll have p1 d1 upon d1 cube is equal to p2 d2 upon d2 cube, right? So here what we'll get by this is the by comparison of the shear stress of both springs is same. So we'll get p1 d1 upon d1 cube is equal to p2 d2 upon d1. Now this is the by comparing the shear stress. Now deflection of both springs is same. We also know that d delta 1 is equal to delta 2. Now what is deflection? 8 p1 d1 cube up, into n1 upon, so it is 8 pd cube n upon gd raised to 4, right? So put that all this 1 and 2 and compare the deflection of the spring. 8 p1 d1 cube n1 upon gd1 d1 raised to 4 is equal to 8 p2 d2 d2 cube n2 upon d2 g d2 raised to 4. So now here 8 will cancel out, and also like g will is same. So the materials of both springs is same, so g will cancel out. So we'll get p1 d1 cube n1 upon d1 raised to 4 is equal to p2 d2 cube n2 upon d2 raised to 4. Now what we have seen that we talked about it, solid length of both springs is same. That means n1 d1 is equal to n2 d2. So what we will try to do here, we will try to see d1 n1 is equal to d2 n2. So what we will do, we will try to see the, just this n1 multiplied by here d1, small d1. So this will multiply here also. So we have to multiply here also. This will become d1 raised to 5. So n1 d1, then d1 raised to 5, right? So we'll get p d1 cube n1 d1 upon d1 raised to 5 is equal to p d2 cube n2 d2 upon d2 cube raised to 5. So what we did here, we multiplied both numerator and denominator by small d1. Here same thing, small d2. So that's why we got d1 raised to 5 and n1 d1, right? But n1 d1 we have seen that solid length. What is solid length? Number of coils into diameter, wire diameter, right? It is same. So this thing will cancel out. So we'll get p1 d1 cube upon d1 raised to 5 is equal to p2 d2 cube upon d2 raised to 5. Right? Now we can use this formula, like whatever we got here, right? We can use this, and then we'll get d1 square, capital D1. So what we are, this is we have got using the deflection, and we have got what here, p1 d1 upon d1 cube, p1 d1 upon d1 cube. So here p1 d1 into d square and upon d1 cube into d1 square. Are you getting my point? So what we will do, we will put here p1 capital D1 into d1 square, right? What we can write, d1 capital D1 cube is equal to capital D1 into capital D1 square, and d1 raised to 5 small d1 raised to 5 is equal to small d1 raised to cube into small d1 raised to 2, right? So that way we, from this equation we know that p1 d1 upon d1 cube is equal to p2 d2 upon d2 cube, and we want to use that here. So combination of this and combination of this, we can get d1 square capital. So here from here d1 square will remain capital D1, and from here small d1 square will remain. So d1 capital D1 square upon small d1 square is equal to capital D2 square upon small d2 square. Okay, so these are the ratio. So we'll take root of both sides. We'll get d1 upon d2, sorry, d1 up capital D1 upon small d1 is equal to capital D2 upon small d2. What is d1 upon d2 is spring index, right? So we can say spring index of spring 1 is equal to spring index of spring 2, right? So since the spring index is same, what we proved here, we proved d1 upon d1 is equal to capital D1 upon small d2. This is spring index of spring 1, spring index of spring 2, and both of them are equal. So we can say C spring index of both springs are equal, and since wall factor is only made of only spring index C, then that's why we can say since the spring index of both springs is same, that's the wall factor of both the springs is same. So K1 is equal to K2. That's what we assumed here, and that is what we proved here. Okay, are you getting what we proved here? In this previous step, we proved that spring index of both the spring is same. Therefore, since K is only dependent on the C and it is same for both the spring, then we can say wall factor is same for both the spring. So K1 is equal to K2. Okay. So now what we'll do? P1 upon P1 upon D1 square is equal to P2 upon D2 square. So P1 upon P2, how we will get this? Now we know D1 upon D. So now we are again going back to this formula. Okay. First we used comparison of the shear stress, right? And we got this formula, and then we use comparison of the what is that deflection. Then we got this formula, and from that we concluded that spring index of the both the spring is same and wall factor of both springs is same. Now again go back to this formula. Here D1 capital D1 upon small d1. Take out the small d1 as d1 cube as d1 square into d. Okay, again I will repeat. We are using the this formula, what is highlighted. P1 into capital D1 upon small d1 cube is equal to P2 into capital D2 upon small d2 cube. Here in the denominator, put d1 cube is equal to d1 square into d1 and d2 cube is equal to d2 square into d2. So that way d1 small capital D1 upon small d1 is equal to capital D2 upon small d2, which will cancel out because of this. All right. So what we are left with? We are left with P1 upon d1 square is equal to P2 upon d2 square. Are you getting my point? Here we are saying d1 upon this small d1 is same is equal to d2 upon small d2, right? So we have P1 upon d1 square is equal to P2 upon d2 square. Okay. So P1 upon D1 square is equal to P2 upon D2 square, or P1 upon P2 is equal to D1 square upon D2 square. So ratio of load in spring 1 to the ratio of to the load in spring 2 is equal to D1 square upon D2 square. Multiply both sides by both numerator and denominator by pi. So pi D1 square upon pi. What is pi D1 square? Area of spring, cross section area of spring 1, and D2 is cross sectional area of spring 2. It is basically area. So load taken by each spring P1 upon P2 is equal to proportional to area of those springs, cross sectional area. So what we conclude from this, that the load taken or load shared by each spring is proportional to its cross sectional area of the wire, right? So at the end of this, what we can say, by comparing the shear stresses and by comparing the deflections, the solid length of both the springs are same, and we get the springs index of both the springs are same, wall factor of both the springs are same, and the load shared by each spring is proportional to its cross sectional area of the wire. Okay. Okay. Now we have to find out the gap C between the two springs. Now assume that inside spring diameter is D2, outside spring diameter is D1, and C is the gap between the two springs. How we can find out C? So D1, mean coil diameter of the outside wire, outside spring, D1 is equal to inside spring diameter, right? This small capital D2 plus D1 by 2 plus D1 by 2, right? On this side D1 by 2, on this side D1 by 2. It is basically D2, sorry, D2. So D2 plus small d2, half on this side, half on this side, plus C on this side, C. So it becomes 2C, right? So basically capital D1 is equal to small d, capital D2 plus small d2, right? Half here, plus 2C plus half d1 here, small d1 plus half small d1 here. So it becomes 1 d1, right? So it is basically d2 d1 is equal to capital D2 plus small d2 plus 2c plus small d1, right? So what we can say, 2c is equal to d1 minus d2 minus d1 plus d2, right? So this will be 1 d2, this will be 1 d1, so this is d1 plus d2, right? So 2c is equal to d1 minus this d2 minus d1 plus d2, right? So what we can say, C is equal to d1 minus d2 upon 2 minus d1 plus d2 by 2, right? So this is the clearance between the two springs. So So this clearance is equal to, is taken as basically generally the, while designing it, we take this diameter clearance 2c. What is 1c on this side, 1c on this side, so it is 2c. It is taken equal to d1 minus d2, difference between the wire diameters. So d1 outer diameter minus d2, we take that as your clearance. So we will put that c is equal to d1 minus d2 here. Okay. Again, I will repeat. From the design of the spring, we got C is equal to capital D1 minus capital D2 upon 2 minus small d1 plus small d2 upon 2. And we take generally what that clearance 2C is equal to small d1 minus d2. And if we compare those, we'll get d1 minus d2 small is equal to d1 minus d2 capital minus d1 plus d2. Or we can say capital D1 minus d2 is equal to small d1 minus d2 plus, this will go on this side, plus d1 plus d2. Or if we see this d1 and this d1 will get added, minus d2 minus d2 will get cancelled. So d1 minus d2 capital is equal to twice d1, or the difference between the mean coil diameters of two coils is equal to twice the smaller, or d1, a larger wire diameter. Right. Now what is d1? D1 is equal to c small. Now we are, see here we have capital and small d. We'll try to put everything in a small. So d1 is equal to spring index into d1, and d2 is equal to spring index in d2. Right. So we'll put it here. So d1 is equal to c d1 minus c d2. C will come out. So d1 minus d2 into c is equal to twice d1. Right. So c minus 2, right, or we can simply say c minus 2 d1, right. So c d1 minus c d2 is equal to 2 d1. So c minus 2 d1 is equal to c d2, or d1 upon d2 is equal to c upon c minus 2. Or what we can conclude, that ratio of wire diameter 1 to 2 is c upon c minus 2. So these are the equations used to find out the force transmitted by each spring. So right, we know what is the force transmitted by spring. These forces are proportional to the areas of the wire. Right, we have seen that the force taken by spring 1 and 2 is proportional to its cross-sectional area, and we also know that d1, the ratio of diameters, is directly proportional to c upon c minus 2. So that way we can, by if we know the spring index, then we can find out the ratio of the diameters. We can find out the load taken by each spring, and we can design the spring. Okay. Okay. So you got it. So what we did in the design of the spring, we compared the shear stresses, we compared the deflection, and then we concluded that ratio of the diameters, spring index is same for both the springs, wall factor is same for both the springs, and ratio load taken by each spring is proportional to its area cross section, and the area of the diameter ratio is proportional to c upon c minus 2. Okay. So this is the theoretical part of the spring. Now we'll take a numerical on this. Okay. A concentric spring is used as a wall spring for heavy duty diesel engine, consists of two helical compression spring having same free length, same solid length. So this is the case now, concentric springs which are one inside the other, but they have same free length and same solid length. So deflection is same, solid length is same, N1 D1 is equal to M2 D2, free length is same. The composite spring is subject to maximum force of 6000 Newton. So we have given maximum force of the spring as 6000 Newton, and deflection is 50 mm. So when there is no load, it is free length, right? But when the load is maximum load is 6000 Newton, that time deflection is 50 mm. So we have given delta, and we also know P. So we know the combination of this, we know the combined stiffness. The maximum torsional shear stress is 800 Newton per mm square. Okay, let me just correct this. So we have given that torsional shear stress is also given 800. Spring index is C. C is given as 6 for both the springs, right? Azimuth of the two spring made of a modulus of rigidity of a spring is 81,370 Newton per mm square. So diameter clearance between the coils is equal to the difference between the wire diameter. So what they are saying, the diameter clearance is equal to C is equal to difference between their wire diameters. So 2C is equal to D1. This is what we talked about. The diametric clearance 2C is equal to difference between the wire diameters. So 2C is equal to D1 minus D2. That's what they are. So we can use these formulas. If 2C is equal to D1 minus D2, then we can say D1 upon D2 is equal to C upon C minus 2. We have to find out axial force transmitted by each force. So we have to find out P1, P2. Wire and mean coil diameter of each spring. So we have to find out D1 D1 and D2. Number of active coils in each spring. So we have to find out N1 and N2. Okay. So let me just highlight this thing. Not highlight, but hide this thing. We'll go step by step. Now, what is given in the formula? In the definition, we know load is P is 6,000, deflection is 50, tau is equal to 800 Newton per mm. So tau is 800 Newton per mm square, delta is 50, P is 6,000. Spring index is given 6 and G is given 81,370. So these are the information what is given. Now we'll try to solve. Now first axial force transmitted by each spring, we have to find out P1 and P2, right? But we know that from this, since diameter clearance 2C is equal to D1 minus D2, so we can use a diameter of wire 1 upon diameter of wire 2 is equal to C upon C minus 2. We can find that out. And once we know that ratio, we know that P1 upon P2 load taken by a spring is the proportional to its area, right? Then we can find out P1 and P2, right? So that's how we will approach this problem. First, D1 upon D2 is equal to C upon C minus 2. C is given as 6. So we know that 6 upon 6 minus 2 is 4. 6 upon 4 is 1.5. So we know ratio of wire diameter is 1.4. So the outside spring will have a diameter 1.5, 50% more than the inside diameter. So P1 upon P2 is equal to D1 square upon D2 square, right? This is from this equation, right? P1 upon P2 is equal to D1 square upon D2 square. So we know D1 upon D2 square is 1.5 square, so 2.2. So ratio of the load taken by spring 1 upon load taken by spring 2. So outside spring will take a load twice of 2.25 times more than the load in the wire 1, wire 2, right? This is, right, inside is 2, outside is 1. Okay. So we know that, if we know the spring index C, then we can find out the ratio of the wire diameters. Once we know that, we can find out the load taken by each spring, ratio of that. And once we know that, we can find out total load, and we can find out individual load, because P1 plus P2 load taken by each spring is P1 and P2, and then total is P, which is 6,000. So we know P1 plus P2 is equal to 6,000. We know P1 upon P2 is equal to 2.25, and then we can simply put it back. P1 is equal to 2.25 into P2. P1 is equal to 2.25 into P2. So 2.25 plus 1 is 3.25. P2 is equal to 6,000. So 6,000 upon 3.25 will be your P2. I will again repeat these steps. P1 upon P2 is equal to 2.25. So P1 is equal to 2.25 into P2, right? Put it here, 2.25 into P2 plus P2. So it becomes 3.25 P2 is equal to 6,000. So P2 is equal to 6,000 upon 3.25. So it will be basically, P2 will be 1846 Newton, and P1 is 2.25 times of that. So you will get 4153 Newton as P1. Okay. And if we add these two, it will come to 6,000, combination of both. So we have found out load taken by each spring, P1 as 4153 Newton and P2 as 1846 Newton. Okay. Now we know load taken by each spring, right? So we completed first part. Now we will try to find out diameters, right? Now since we know C, we can find out, because both of them are having same C. So wall factor is 4C minus 1 upon 4C minus 4 plus 0.615 upon C. So it becomes 1.2525. So we know like wall factor is 1.2525. So shear stress tau is equal to K into 8 P1C upon pi D1 square. Now here C is spring index, K is wall factor, it is same, and shear stress is same. So we can say shear stress 800, it is given, right? 800 in both springs is equal to 1.2525 into 8 into P1 load taken by spring 1, right, into C upon D1. So by using this formula, we can calculate the diameter of the D1, diameter of the outer spring. It is 10 mm, and the corresponding mean coil diameter capital D1 is equal to 6 into 10, that is 60. So outside spring will have a diameter of 10 mm and mean coil diameter of 60 mm. Right? So similarly, we can use the same approach to find out the inner coil, right? So again 800 same K, but P will be different, right? So that time D2 will be. So again, like, we can use this formula also, D1 upon D1 square. We can use this formula also here, right, to find out the diameter of the coils. You can use this P1 upon P2 is equal to D1 square upon D2 square, right? Okay. So now this inner spring will have diameter of, using this same formula, inner spring will have diameter of 6.65. So we will take 7 and corresponding mean coil diameter will be 42 mm. So we have we know the diameters of the coils D1, D2, capital D1, capital D2, 10 and 60, 7 and 42. Now we'll try to find out number of so what we did, we completed second part, wire diameter and mean coil diameter, right? D1, small d1, capital D1, small d2, capital D2, right? We use the shear stress formula, tau is equal to wall factor into 8 pc upon pi d1 square, right? Now number of active coils. Now for that we have to use the equation for the deflection of the spring. Okay. Now deflection of the spring delta is equal to 8 p d cube n upon g d14. Right. Here delta deflection of the both the springs is same. So load is different, diameter is different, number of coils is different. Right. So we know all the diameters now except for the n. So deflection delta is equal to 50. That is what is given, is equal to 8 P1 D1. P1 is given 4153. We have calculated. D1 is 60. We calculated. And small D1 is 10. So with this, we can get the number of coils as 5.67. Now, so we'll have 6 coils of, for the spring 1. And if it is grounded ends, right? So if the ends are grounded, then we will just have square and grounded, right? Then we have to add 2. These are the active coils. Add to get the total coils. So total coils will be 6 plus 2, 8 coils, right? Similarly, N1 D1 NT into what you can say, N1 D1 is equal to N2 D2, right? So 8 into 10 diameter of this is equal to NT2 into 7. So we get 11.43 or 12 coils. So number of total coils for the spring 1 is 8. It is larger spring. Number of total coils from inside spring is 12 coils. And these are the total coils, right? Because this is NT we are using. So number of active coils will be 12 minus 2, 10. So this is 10 coils will be active coils for the spring 2. Right? So for a inner spring, outer spring, the number of active coils will be 6. For outer spring, so inner spring, the number of coils will be 10. Okay, that's how we will design a concentric spring. Okay, so we have completed this part of concentric springs. We'll simply go in a few minutes. We'll go through what is surge in a spring, and then we will stop for today. And then tomorrow we'll have last lecture. Okay. So now, what is surge in a spring? It is basically a concept. Surge means like if you know in a home equipment, when we say surge protector, we use a equipment or instrument called surge protector. Means if your voltage goes too much high, if your current is flowing in a very heavy way, or if it surges, that means it reaches the peak and crosses it. That time we call it is we want our electrical equipments to be protected, and then we use a surge protector. That means it will not allow to go it up beyond certain point. That time it will have some kind of safe fail system. It will break the fuse or something like that, and it will stop working. But it will not allow that high voltage to pass or surge in the your current to pass, and to damage your electrical equipments. So similarly, in springs also something called a surge is there. Now, what is this surge? Surge happens when the natural frequency of your spring matches with your frequency with which it is operating. Okay. Now I said few things, but let's revise what are those things. Now you are going to use the springs to basically take the load or take the shock, absorb the shock, or to have some kind of force applied, right? In a cam, right? In a cam you will be basically applying the force. You are going to put it back. So it will have different applications for the spring, right? But if the application is cyclic, means it is going to happen again and again and again. Compression, expansion, compression, expansion, compression, expansion. If it is happening again and again, then we can say it is having a cycle. So it will have some kind of frequency. Frequency means in 1 minute it will be having this cycle 20 times, 30 times, 300 times, 3000 times. So each spring will have this kind of a cyclic what is the working. So if it is force is applied is cyclic, then that cyclic force, or it will basically we have some kind of frequency. Means what? It will have per second. It will be going through that cycle how many times? Now, what is frequency? Frequency is number of cycles per second, right? Per some unit time. So, if we take second as the unit of time, then number of cycles of that compression and expansion, that number of cycles per second is called as frequency of the spring, external frequency of the load, right? So we have some kind of frequency of the external load, right? So that means it is getting, it is going under that action per second how many times. This is one frequency. Now there is something called as natural frequency. You must have learned it many times. Natural frequency is the frequency of any object, right? With which it naturally vibrates, right? If we do not apply any external force, it will have some frequency with which it will naturally vibrate. That frequency is called a natural frequency. Now, when this natural frequency of any object matches with the external frequency or the external forces frequency, that time it will fluctuate or it will vibrate with very high amplitude. It will shake rigorously, and that is called as resonance. Okay, so this same concept will happen in spring also, and that concept is called as surge in the spring. Are you getting my point? So when the natural frequency of your spring matches with the external frequency of the force, that time the spring will have undergo some concept called as surge on the spring, right? So something like wall springs, where there is a cyclic load is applied or the periodic force is applied, that time your spring will go under surging. Now, how this will happen? Now, when we apply load on the spring, okay, it will take the load, it will pass the load to the extreme end of the extreme end coil, and that will again come back. Okay, so it is kind of wave. When the spring comes into action, when the load is applied, it will have kind of what you can say shock. It will absorb the shock. It will pass the wave to the bottom end or to the extreme coil. It will again come back. So this is one cycle of the spring. So it will have this kind of cycle depending on the external load. So when this external load cycle matches with the natural frequency of your spring, that time surge will happen and your spring will vibrate very rigorously, and it might fail because of the high stresses or because of these extreme fluctuations, right? So these also this is not desirable because your spring will fail because of the resonance. Okay, so it will have very high stresses and it will fail because of the fatigue. Because of this very high stresses, it will undergo fatigue and it will fail. And this is not expected, or this is not what you can say, it should we try to avoid it, right? So how we can avoid this is a surge in the spring? We can avoid by changing the frequencies of, like, either change the natural frequency of your spring or change the frequency of your application of the load, right? So, in case of wall springs, this is the main case of the failure. Like surging means what? Your frequency is matching with the natural frequency, and because of that, it is going through very high amplitudes, high resonance, and because of that, it is failing because of the fatigue failure. This is the main reason for the failure of a wall spring. Okay. So how we can avoid it? So we can avoid it by, as I said, by changing the either natural frequency or the frequency of the load, right? Now, natural frequency of the, if we put your spring between two parallel plates, the natural frequency is given by W. Natural frequency is equal to half of root of K upon M. K is stiffness, M is mass of the spring, K is stiffness of the spring, right? So it 1 by 2 root of K by M is your natural frequency of the spring. If the one side is flat and other is free for the spring, one end is free and one end is flat plate, that time it is half of it, like it is 1 by 4 into root of K upon M is your natural frequency, where K is the stiffness of the spring, M is mass of the spring. Okay, M is mass of the spring in kg, right? It is not weight, it is mass. So these are the natural. So we can find out the natural frequency of the spring if we know the stiffness of the spring and if we know the mass of the spring. Stiffness is like load upon deflection, right? But load is here is in Newton, right? And here mass is taken in kg, right? The mass of the spring is given by what? M is equal to AL rho. Now what is this AL rho? A is area of the cross section area of the spring, pi by 4 d square, right? D is a wire diameter. L is length of the spring and rho is density of the spring. So A into L is your volume of the spring, right? Area of the cross section into length of the wire, right? This is the total volume of the wire. If you consider a cylinder, pi by 4 d square into L, consider it as a cylinder, right? Multiplied by rho is your density. So pi by 4 d square will be your what is the cross section area of this pi by 4 d square cross section area. Length of the spring L is pi dl. Pi d is mean coil diameter into pi, it is circumference into nt, number of turns or coil or number of coils, right? And rho is density. So, and mass of the spring is given A L rho. If we know the coil diameter, if we know mean coil diameter, if we know active number of turns, and if we know density, we can calculate mass or weight of the spring, right? So, if we know the spring, if we know the stiffness of the spring, we can calculate the natural frequency, right? And this is now how we can avoid it. Like we design the spring such a way that natural frequency of the spring is 15 to 20 times more than the frequency of external. So if we know the external force frequency, it is if it is getting applied by in 20 times per second, so our natural frequency of our spring will make it 20 times or 15 times. So we'll have 300 frequency of 300 hertz, means 300 times per second. Okay, I will again repeat. If our spring is getting compressed and extended 20 times per second, in 1 second 20 times it is happening, so we will make our spring natural frequency 15 times more. 15 into 20 is 300. So 300 times per second, that means 300 hertz. So our spring's natural frequency will be 300 hertz. Okay, this will avoid the resonance. Okay, sometimes we'll provide the frictional dampers for the center coil to avoid the surge, right? And the spring made of standard wire reduces the surge, right? So if we use the standard wire, that time it will reduce the surge of the spring. So we can use these some ways to reduce the surge in the spring. Right? So surge is very important and serious problem, for the walls where cyclic load is there, right? So that time by using these kind of applications, these type of changes, we can avoid the surge. For when the load is steady, it is not it is not cyclic. That time surge is not. Surge comes only in picture when frequency is there, cycle is there, right? For the steady load, the load is when we apply the load and it is remaining same. That time the surge will not come into picture. Okay. So this is about the surge. I think again we are done with the time, so I will stop here. And next lecture will be our last lecture. That we will go through design of a multi-leaf spring quickly, and design of not design but only theoretical part of a torsion spring. So torsion spring and multi-leaf spring, designs of those will take in the next lecture. Okay. Okay. Thank you guys for attending, and put your attendance, and see you in the last lecture of this DME-I. Okay. Thank you. Thank you guys. Uh, See you next time.